In this module, we're going to talk about finite state machines, which are one of the most common sequential circuits that we're going to build. So first we'll talk about generally synchronous sequential circuits. Then we'll talk about finite state machines. Give an example. Overview what the design procedure is for FSMs or finite state machines. And then give another example of a finite state machine. So here's a sequential circuit. So a sequential circuit, so this general class consists of all circuits that aren't combinational. So here's a circuit. We have 3 inverters back to back, and then with feedback. And so when X goes high, Y is going to go low, and Z is going to go high. So when X goes from 0 to 1, well, Y is going to go, where it's going to see that 1 and go from 1 to 0. And then Z rises to 1, and that drives its output to 0, which drives this back to 0, which drives this back to 1, which drives this back to 0, which drives us back to 1. So because we have an odd number of inverters that are strung together with feedback, this is an unstable circuit because it's going to basically oscillate. So if you look at X, Y, and Z on a timing diagram, remember time is on the X-axis. If we look at X, it's going to oscillate as driven by the feedback here, and Y oscillates and Z oscillates. So this circuit has no inputs, 1 to 3 outputs. So the outputs could be X, Y, and Z, or just one of those. But it's astable because it oscillates. Our period depends, so how the period is how often it repeats. So there's one cycle or one period. Depends on the inverter delay. So this has the cyclic path from the output fed back to the input. So here's our cyclic path. So it's problematic in that, well, we don't have any inputs to control it, and the delay, the oscillation, right, this period, may actually vary depending on this inverter delay. And as we talked about before, delay varies. So delay varies in terms of, well, where is that inverter placed on the chip? Temperature affects the delay of an inverter or any logic gate, etc. So we're going to confine ourselves to synchronous sequential logic design. So synchronous sequential logic, synchronous to the clock. So we're going to always have a clock in our circuit, and this clock is basically inserted into our circuit by inserting registers, or register is another word for D flip-flop. So registers into our circuit. So we break up cyclic paths by inserting registers instead of just having, some combinational logic. That's combinational logic with a cyclic path. We're going to actually break that up with a register. So we can still have a cyclic path, but it's broken up by that register. So we don't do this, but we do break our cyclic paths with a register. This register contains the state of the system, and our state changes at the clock edge. So the system is called synchronized because it's synchronized to the clock. That state's only going to change at the clock edge. So I'm going to talk about these high-level rules of synchronous sequential circuit composition. It'll make more sense once we do an example. So just, we're going to go over it, keep it in the back of your mind, and then when we come back to it, it will make even more sense. So here are our rules of synchronous sequential circuit composition. Every circuit element is either a register or combinational logic. We have at least one register in our system, and all registers receive the same clock signal. And the last one is the one we started with, that every cyclic path contains, so here's a cyclic path, it contains at least one register. So the two most common synchronous sequential circuits are finite state machines, or FSMs for short, and pipelines. So we're going to talk about FSMs in this class, and you'll talk about pipelines in later classes like CpE 200, 300, and 404. Okay, so let's talk about this first kind of synchronous sequential circuit, the finite state machine, or FSM. So FSMs consist of a state register. So here's our state register that contains the current state. So it holds that or stores that value. And this input on the left side is called the next state because at the next rising clock edge, that next state is going to become our current state. So we have a state register that stores the current state and loads the next state at the clock edge. So loads it loads it into its internal storage. We also have combinational logic. Well, one of our combinational logic blocks computes the next state. So given the current state and inputs, what's the next state? And the second computes the outputs. So here's a overall view of our finite state machine. We have a state register that stores the state or current state. So state equals current state. So just for short, we'll call the current state the state of the system. And given this state, we have some output logic, some combinational logic, given the state as inputs, that computes what our outputs should be. Also, given the current state and the inputs, we can compute where the system should go next. So what the next state is. So this is called a Moore type FSM, where the outputs depend only on the current state. Just so you're aware of it, there's another type of FSM, the Mealy type FSM. Mealy FSMs, the output depends on both the current state and the inputs. We'll talk about that kind of FSM in CpE 200. So for now, don't have to worry about this one, just so you know it's out there. We're going to focus on the Moore type FSM. Okay, so let's go through an FSM example, and then we'll come back to that overall picture of what an FSM looks like. And again, with an example, that overall picture will make more sense. Okay, so let's suppose we want to build a finite state machine that helps us organize our day. So we want to make sure that we, wake up and the right time and eat breakfast and, go to class and things like that. So we're going to build this finite state machine to help us do that. So let's start with some state. We'll start with the wake up state. So these circles indicate states. So the circles indicate states in our finite state machine. The word finite, well, it's not going to be an infinite number of states. It's going to be some small number, in our cases 4 to 10 states. And, it can be more than that, but it's a finite number of states. So we have the wake up state. So W equals the wake up state. And now we have some input T to our system, time. It says, oh, hey, if we have time when we wake up, let's go ahead and eat breakfast. So then we'll go into the eat breakfast state. And these arrows indicate transitions between states. Okay, so that's cool. If we don't have time, well, then we, get up and maybe we brush our teeth. We go to the brush teeth state. And after we eat breakfast, either way, so this transition doesn't have any input on it. And that means independent of what happens at the next clock edge. We're going to go from the eat breakfast state to the brush teeth state. Okay, so transitions may have inputs on them. Transition with an input, or they may be independent. And these transitions happen at the clock edge. Okay, so if we're in the wake up state and we get a clock edge, well, first we have to, before the clock edge, we have to test and see, hey, do we have time? Or maybe we have a buzzer or something, or we just look at the clock and it says, oh, yep, you do have time. You have some input that says, yep, you have time. Go to the eat breakfast state. So the next clock edge transitions to the eat breakfast state. And then well, independent of anything, actually, this one doesn't have anything on its arrow, on its transition arrow, at the next clock edge, no matter what, if you're in the eat breakfast state, you go to the brush teeth state. Okay, so now after the brush teeth state, maybe at that point we go to the class state, so going into class. Okay, and then just to make it easy, maybe at that point we go back to the wake up state, but we're not going to talk about any implications of that. So, all right, so we have this finite state machine. This is our complete finite state machine with 4 states. We have the wake up state, the eat breakfast state, the brush teeth state, and the class state. And then we have transitions between states. In this case, we only have a single input. We have the input t, or time. And we always, always, always have to have a reset input. So remember, when we start this circuit up, this is going to end up being a circuit, we have to know what state it's in. So when reset goes high, we have to go to some known state. And so this arrow showing the reset input going to a state, that's the state it's going to go to upon reset asserting, either synchronously or asynchronously. Okay, so we started with this is called a state transition diagram. It shows our states and our transitions between states. So we have our state transition diagram, and now we're going to write a state transition table. So here is our state transition table. That's our next step. You can kind of see that this state transition table is going to look a lot like a truth table. So we have our current state, and our inputs. In this case, our single input is going to determine what our next state is. So if we're in the wake up state and we don't have time, so t is equal to 0, we should go to the brush teeth state, the B state. So here we go. In the wake up state, no time, we go to the brush teeth state. However, if we're in the wake up state and we do have time, the next state should be the eat breakfast state. Okay, so now we can go on and say, well, what if we're in the eat breakfast state? What should the next state be? Well, independent of inputs, or no inputs here on that transition, the next state at the next clock edge should be the brush teeth state. Now, if we're in the brush teeth state, independent of any inputs, we should go to the class state at the next clock edge. And then finally, the last one, if we're in the class state, independent of inputs, we should go to the wake up state at the next clock edge. Okay, so that kind of looks like a truth table. We have some stuff on the left and some stuff on the right, but those are letters and not binary values. Well, we can now encode these using binary values. And so we can choose encodings. The most common encoding is to choose binary encoding. So we can say, well, we have 4 states we need to encode 4 different things. So we need log base 2 of 4, we need 2 bits. So we can say, okay, the wake up state is 0, 0, the eat breakfast state is 0, 1, brush teeth state is 1, 0, and the class state is 1, 1. So here are state encodings, and we call this state bit 1, and this state bit 0. So now we can encode this basically state transition table, which is basically a truth table, and we can get our current state, state bit 1, state bit 0, our inputs, in this case t, and encode this to get our next state. So our next state we write as s sub 1 prime, so we're overloading that prime symbol, and when we type that means bar. In this case it means next state, and s sub 0 prime. Again, that no longer means bar, it means next state. And so we can just take these one row at a time and say, okay, well that top row, W, the state encoding was 0, 0, or is 0, 0. So we'll put 0, 0 for W. T is 0, and the next state should be B. We look at that, 1, 0 is the encoding for B. Okay, in the next row, we just encode that. W, again, is 0, 0. This time is 1. And the next state should be E, which is the 0, 1 state. Now we take the next row, encode that, E. We look up at our state encodings. Always write those down so you can keep track of them. E is 0, 1. Don't care what T is. The next state should be B. Look up and see our encoding for B is 1, 0. Next row, we have B. Again, B is 1, 0. T is a don't care. And C is 1, 1. Now we have C again is 1, 1. Don't care on our inputs. And W is 0, 0. Okay, so that looks a lot like a truth table. We have some values, binary values and don't care on the left, and some values on the right. So our next state is determined by, our next state bits here on the right are determined by our current state and our inputs. Okay, so now we can write equations for that basically that truth table, for that state transition table. This is the encoded state transition table. We also call this the next state table. Now we can write next state equations, so equations for our next state bits using our encoded state transition table or our next state table. So we have 2 next state bits, S1 prime and S0 prime. So S1 prime is going to be equal to, I just take these ones, sum of products. So the top one we're going to get S1 bar and S0 bar and T bar. Or, here's our next one, S1 bar, S0, T is a don't care, or S1 and S0 bar. So you could pop this into a K-map, or we can take a look at it otherwise and see that, okay, well, I could use covering here between these two terms, for example, to get rid of, in this case, the S0 term. So this term covers S1 bar, S0, or S1 bar, S0, and T bar. We'll bring this other term down. S1 bar, S0 bar, T bar. And then we don't forget to bring down the last term, or S1, S0 bar. And so now we combine these two terms here to get, well, S0 bar is combined out. So we get S1 bar, T bar, or, well, we're left with these two, S1 bar, S0, or S1, S0 bar. And we can see that this is the XOR relationship. So we're going to get S1 bar, T bar, or S1 XOR S0. Just allows me to use one gate, an XOR gate, instead of two AND gates and two inverters. Okay, so there's our next state equation for S1 prime. And now we can write the equation for the second output. S0 prime is going to be equal to, well, that one. That's going to be S1 bar, S0 bar, and T, or that one, again, sum of products, S1, S0 bar. So again, we can use covering to expand that second term. We're going to get, well, our first term, our original term, S1 bar, S0 bar, and T, or S1, S0 bar. We're going to use covering on that second term, S1, S0 bar, to try to get rid of something there. Well, they already differ in S1, so I have to AND that with T. I expanded the S1, S0 bar term to get S1, S0 bar, and T. And now I'm going to combine these two terms. Well, S1 combines out, and we're going to get equals S0 bar and T, or S1, S0 bar. So here I've redrawn our state transition diagram. So here I've redrawn our state transition diagram and our next state equations from the prior slide. And now we're going to implement this into a circuit, a synchronous sequential circuit. So when we build an FSM, we always start with the flip-flop or the register that holds the state. So we'll draw our state register. In this case, we have two state bits, S1 and S0. We always put our clock in here. And then we also have a reset input that's connected to our reset signal. So when reset goes high, so when reset asserts, the state bits, S1 and S0, are going to reset to 0. We're going to get into a known state, and particularly the 0, 0 state, which is the encoding for the W state. Okay, so I've drawn our state encodings here on the upper right so we can remember how we encoded those different states. So we're going to take our state bits and feed them back around onto the other side of our register, our state register. And sometimes I label them again. These are not inputs. They're just labels to show that these are the outputs from the state register, S1 and S0. We're going to use our current state, S1 and S0, as well as our inputs. In this case, we have a single input, T, to determine, using combinational logic, what our next state should be. So our next states, S1 prime and S0 prime, are on the left side of our state register because at the clock edge, those next state bits will become our current state. Okay, so let's draw our logic gates that we need to create these next state outputs. They're going to be fed as inputs to our state register. So we start with S1 prime. First we need S1 bar and T bar So we need an AND-shaped gate with bubbles on its input tied to S1 bar and T bar. And that's going to be ORed with an XOR gate, output, the XOR of S1 and S0. So S1 XOR S0. Okay, so we've gotten the logic for state bit 1 prime, so the next state bit for state bit 1. And now let's draw the logic for S0 prime. So we have an AND-shaped gate with one inverted input. We get S0 bar and T. That's ORed with another AND-shaped gate with one bubble on its input. We get S1 and S0 bar. Now we've built our finite state machine using logic gates. So let's test this finite state machine using a timing diagram. So we'll simulate it on paper. So let's take a look at what happens. So we'll have a clock. And we'll also have a reset input. So reset. And we'll reset it at the beginning of our simulation. And now we want to look at what the state bits are. So we also want to put time in, so randomly choosing what time should be. So we have time for a while, and then we stop having time. Now let's look at what S1 to 0, what our current state is. So S1 colon 0. Well, when reset is 1, if it's synchronous at the clock edge, it gets reset to a known state, and particularly the 0, 0 state, which is W. We'll draw our state bits here. So this is the 0, 0 state, the W state. And when we have multiple bits, we will show it as this kind of block showing state bit 1 and state bit 0 together. So they're both a 0 in that case. Before the clock edge, if it's a synchronously resettable flip-flop, it's an unknown state. Okay, so reset is high at that point, but at this clock edge, reset is low, and so we need to know what the next state is. So when the state is 0 and 0, the W state, we can look over here and feed this through our logic circuit and see what the calculated next state is. So we have 0 on S1, 0 on S0, and we have a 1 on T. So here's 1 on T. So this next state, these next state bits are getting calculated. So let's see what those are. We expect it to be, if there's time, and we're in the W state, we expect it to be E, the 0, 1 state. Let's see if that actually happens. So we get 0 bar, so S1 bar, which is 1, and a 1 bar, which is a 0. So we get a 0, so we get 0 or, well, 0 XOR 0 is also 0. So S sub 1 prime is going to be 0. So far so good. So at the next clock edge, we're going to get a 0 here as the S sub 1 prime. Now let's see the bottom one. So we get S0 bar, again 1 and T, which is 1. So we're going to get a 1 or something. I don't even need to evaluate the bottom one. 1 or anything is 1. And our next state bits are 0, 1. At the next clock edge, those next state bits become the current state. And we get our state, in fact, is the E state, the eat breakfast state. And that's exactly what we expected. If we were in the W state, reset is low, so reset goes low here. We do have time. We expect the next state to be the E state. That is in fact what we calculated here. And at the clock edge, that next state became the current state. Okay, so now we're in the 0, 1 state, the E state, and independent of time at the next clock edge, we expect to transition to the B, the brush teeth state. We look over here and we say, oh, that's the 1, 0 state. Let's see if that happens. We feed over our current state, 0, 1, and we can see, well, let's see, time is still 1 here, so we get 0 bar here, 0 bar is 1, and 1 bar is 0, so we get a 0 on that top and shape gate. It's really a NOR gate. And then we get S1 XOR S0, so 0 XOR 1, we get a 1, so we get 0 or 1, S1 prime is 1. And on the bottom we get 1 bar and something. So here's our 1 bar. Well, 1 bar is 0, or something is going to be 0, and something is going to be 0. And here we get 0 and something, well, anything and 0 is going to be 0, and so we get a 0. So at the clock edge, so that's our calculated next state. So at the clock edge, that next state becomes the current state, and we're going to get the next clock edge, we're going to get it to transition to the 1, 0 state. And in fact, that is the encoding for B. And that's exactly what we expected. So now the current state is the B state, and we expect that at the next clock edge, the current state will become the C state. So let's see what happens. So B, we're in the B state. We're in the 1, 0 state here. And so let's see what happens. We expect to go into the 1, 1 state, into the C state, given our state transition diagram. Let's see if that happens. So we have 1 bar, right here is 1 bar. We have a bubble on that input. So we have a 0 here, just to the right side of that bubble. 0 and something is going to give us 0. And here we have a 1 XOR 0. Give us 1. So we have 0 or 1. S1 prime is 1. And now we get S0 bar from this one, so that's 1 on the other side of the bubble. And T, well, T at this point is 1, or S1, which is 1, and S0 bar, so we get 1, and 0 bar, which is 1, we get 1 and 1, we get 1, so we get 1 or 1. In fact, we get a 1 on our S0 prime. So our next state transitions to, at the clock edge, transitions to, well, this next state becomes our current state, and our current state becomes 1, 1, which is the class state. And we can keep doing this. Next clock edge, we can see again what it calculates. We expect that to be 0, 0. Here we get 1 bar to 0, and, well, time is still 1 at this point, so 1, well, it doesn't even matter, right? 0 and anything is just 0, so we get a 0 here. S1 XOR S0, we get a 1 XOR S1, S0, which is a 1. Well, 1 XOR 1 is 0, so we get a 0 up here as expected. And then we get T, which is 1, and S0 bar, well, S0 is 1, so S0 bar is 0, so we get a 1 and 0, gives us a 0. Here we get a 1, S sub 1, and S sub 0 bar, well, S sub 0 is 1, so S0 bar is 0. We get 1 and 0, it's also 0. 0 or 0, we get a 0. So, as expected, we transition to the 0, 0 state, which is the wake up state. Okay, so now we've built this finite state machine, and we've built it using circuits. So it can control, well, given the current state and the inputs, what's our next state supposed to be. Right now, with this circuit, we don't have any outputs. So let's add some outputs to our system. Let's suppose in the class state, for example, let's suppose that we have some output, like H is our output for like a happy LED goes off. H output turns on and some LED turns on and says, oh yeah, happy because we're in class and we're learning some cool stuff. Okay, so now you'll see this output is completely determined by what state we're in. And so we can look at our output, we can actually plot our output here, our happy output. We can see that that happy output should only go high at this point when we're in the class state, and then it goes low, dot, 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 right, dot, dot, dot for all of these. And so we can write what's called an output table. It has just the current state on the left and the outputs on the right. So our current state, in fact, we can encode this, but we can also just go directly to our state bits. S1, S0, our output in this case, we have a single output H, 0, 0, 0, 1, 1, 0, 1, 1, and our output in this case should be 0, 0, 0, only true in the class state. And again, if you want, you can, write this in an encoded way. You could write this as current state, outputs, and you could write this as, well, first we're going to say W, E, B, C, those are our different states, and the output should be 0, 0, 0, 1, our output H. And then we can encode it. Fine if you go directly to the encoded version of the output table. Okay, so can we write an equation for this? Yeah, certainly. This is now old hat. We have a sum of products implementation of this. We can say H is equal to S1 and S0. So we add this gate onto our output here. Here's our output logic. And H is going to be 1 when S1 is 1 and S0 is 1. The output, you can see, is completely determined by just the current state. So now if you look back at our general picture of our finite state machine, you can see the overall pattern. So we have a state register with a clock, and it should always have a reset input. We have some next state logic that determines from both the current state and the inputs what the next state should be. The output logic, in our case we just had a single AND gate, the output logic determines, just given the current state, what the output should be. So we have our state register, our next state logic that determines from the state bits and the inputs what the next state bits should be. And we have our output logic that determines, given just the current state, what the output should be. So again, remember, the next state is determined by the current state and the inputs, and the output depends only on the current state. So our output table will always have just the current state on the left and the outputs on the right. It never has the inputs in the output table. Okay, so let's step back and talk about the design procedure that we just went through for our finite state machine. So we identify our inputs and outputs. In our case, we always have clock and reset as inputs. So clock and reset are always inputs to our finite state machine. always, always. And then our other inputs are, well, in our case, we had a single input time and a single output h. And those internal signals, the state, for example, and the current state and the next state, those are internal to the FSM. Those are not inputs or outputs. Those are internal signals. So just as we did, the next step is to sketch the state transition diagram, then the state transition table, choose encodings, and rewrite the state transition table with our encodings. We also write an output table with the current state on the left and the outputs on the right. And finally, we write our Boolean equations for our next state and our output logic, given our two tables. Remember, this state transition table is also called the next state table. And finally, we build our FSM using a circuit schematic. Start with our state register, bring our state bits around, bring in our inputs, implement our next state logic using our inputs and our current state, and then also use our current state to determine what our output should be. Also, never forget to put clock and reset connections to your state register. So let's go through another example of a finite state machine. This is a traffic light controller, and this one's also in your book. So if you want to read about it, you can also use the book as a reference. So let's suppose we have two inputs, which are traffic sensors, TA and TB. So they're going to determine whether we have traffic on Academic Avenue. T sub A will determine that traffic. Or Bravado Boulevard, so TB will determine if there's traffic on Bravado Boulevard. And we also have lights on each of these different ways. So LA is the light for Academic Avenue, and LB is the light for Bravado Boulevard. So we go through our steps. We can first draw the black box representation of our circuit. We have clock and reset always as inputs. And then we have our additional inputs, TA and TB, our traffic sensors, and our outputs, LA and LB, to determine what those lights should be, red, yellow, or green. So we want to make this FSM, basically, we want to start it off so that Academic Avenue has the green light. So it starts off with Academic Avenue having a green light and Bravado Boulevard having a red light. That's the initial state. And as long as there's traffic on Academic Avenue, we want to stay in this state. As soon as there's no more traffic on Academic Avenue, all of the cars have passed by, then we want to transition so that Bravado Boulevard then gets the green light and Academic Avenue transitions to getting the red light. As long as there's still traffic then on Bravado Boulevard, we keep that state of Bravado Boulevard getting the green light. And then as soon as there's no more traffic on Bravado Boulevard, we transition to the original state of Academic Avenue getting the green light and Bravado Boulevard being red. Okay, so remember that we have our states, which are in circles, and transitions, which are arcs. So we start at our reset state. We always, always, always have a reset input, so we know where we can start at on our FSM. So we'll call this S0. This S0 is not the same as state bit 0. S0 is just indicating this is a state called S0. So just like we had W, B, E, and C in the last FSM, S0 is just the name of the state. Okay, so in state S0, we want to have LA be green. So Academic Avenue has a green light, and LB is red. Okay, and we want to stay in this state. So on the next clock edge, we want to stay here as long as there's traffic on Academic Avenue. As soon as there's not traffic on Academic Avenue, then we want to transition to a new state. We don't immediately make LE red and LB green. so that we avoid collisions, but we're going to go to an intermediate state. We'll call this S1, where LA is yellow and LB stays at red. So that we avoid collisions. And now, independent of any inputs, the next clock edge, suppose our clock is, has some maybe 3-second period. So the clock edge is the period of the clock. We call this the clock period. Maybe the clock period is 3 seconds or something. So we give it 3 seconds to have a yellow light, or 5 or whatever. And then at the next clock edge, we transition to state 2, state S2, where LA is now red and LB gets the green light. And so we want to stay in this state as long as there's traffic on B. But as soon as there's no traffic on Bravado Boulevard, we want to transition to state 3. Again, we don't immediately want to go to giving LA the green light and LB red, just to avoid collisions. So we'll get LA still red, but LB is going to transition to yellow to give time to make it through the intersection. And then, independent of any input at the next clock edge, we'll transition back to state S0, where there's a green on Academic Avenue and a red on Bravado Boulevard. And here it is written out nicely. Again, if it helps you for these, you can write TB equals 1. And this is the TB equals 0. No more traffic on Bravado Boulevard. Likewise for TA and TA bar. So TA equals 1 here, TA equals 0 there. But it's more concise to put TA and TA bar. Okay, so now we can write our state transition table, also called the next state table. We have our current state and our inputs on the left, and our next state on the right. So if we're in state S0, we look at our state transition diagram. If TA is low, we go to S1. If we're in the S0 state and TA is 1, however, still have traffic on Academic Avenue, the next state is S0. So we stay in the S0 state. All right. So if we're now in S1, for these state transition tables, we just consider each state independently. So when I'm in S1, I don't have to think about S3 or S0. I'm in S1, kind of, a Zen type thing. Stay in the current state, stay in the present, and don't worry about S0, S2, and S3. If we're in S1, where do we transition next? Well, if you're in S1, independent of any input, on the next clock edge, it's going to transition to S2. Okay, and now we look at what happens if we're in S2. For S2 and TB is low, then we're going to transition to S3. If we're in S2 and TB is high, so there's traffic on Bravado Boulevard, and we're going to stay in the same state. We're going to stay in S2. Now S3, independent of any inputs at the next clock edge, if we're in S3, next clock edge, we're going to transition to S0. So now we have this written nicely. Now the next step is to encode our states. And so we can use, again, binary encoding. We have 4 states, so we're going to need at least 2 bits. If we had 5 states, we'd need another bit. We wouldn't use all of the encodings, but for 5 states, I need more than 2 bits. I need 3 bits. For up to 8 states, I can use 3 bits. Once I get to a 9th state, now I'm going to need 4 bits to encode my states. Okay, so for this case, we have our 4 states, we need 2 bits, and we choose binary encoding. So state S0 has encoding 00, S1, 01, S2, 10, and S3, 11. Again, these are state bits 1 and state bit 0. So S of 1 is not equal to S state 1. Likewise, S of 0 is not equal to S0. These are state names, state S1 and state S0, and these are state bits. So we look to our prior table and we just start encoding them. So S0, we replace those with 00. State 1, we replace with 01. So they're the correlation. S1, I'm going to replace with the binary encoding for 1. 0, state 0, I'm going to replace with the binary encoding for 0. State 2, 1, 0, 2, binary 2, and then state 3. Okay, so now we just go to our prior table. So S1, S0, S2, and S3, S2, S0. S3, S2, S0. It's better to do those side by side like we did in the last one, but we can also flip between slides too. But on paper, you should do those next to each other, so it's easier to go from the unencoded state transition table to the encoded state transition table. So here we have it filled out nicely, and now we can read off what these equations are. So I'm going to show 2 different ways to do this. First, I'll start with the original method that you learned, which is the sum of products method. So S1 prime, we're going to start with the 1s, so sum of products. S1 prime is equal to, well, S1 bar and S0, both the inputs are don't cares. So S1 bar and S0, or the next one is going to be S1 and S0 bar and TB bar, S1 and S0 bar and TB bar, or the last one is S1 and S0 bar and TB. So we can see that we can use combining for these last 2 terms and get just S1, S0 bar, and we bring down our other term. So we get S1 prime equals S1 XOR, that's the XOR function. So S1 XOR S0. Why do I write it with the XOR function instead of our minimized sum of products? Well, it's just easier for me to implement it with a single gate, a single XOR gate, instead of 2 AND gates, inverters, and an OR gate. Now we can do the same thing for S0 prime, read it in sum of products form. We're going to get S0 prime is equal to S1 bar and S0 bar and TA bar. Or S1 and S0 bar and TB bar. Okay, so the second method that we could use, so this is method 1 using sum of products. Because there are 4 or fewer, inputs to our truth table, so variables on our left side of our truth table, we could use a K-map as well. We could use that to reduce our equations as well. But this method is pretty straightforward and pretty simple. So whichever way you prefer is fine. You need to be able to do method 1 because we may have more signals on the left-hand side than 4. So K-maps may not always be usable. Never, ever, ever use Klein-McCluskey method unless you're asked to. Quine-McCluskey method is a lot longer, even than using Boolean algebra for reduction. So we also need to have an output table. So we go back and look at our state transition diagram, and we can see that our outputs are completely determined just by which state we're in, so what the current state is. We need to encode those outputs. They're not binary outputs, just on or off, or even green and red. If we had two values, we could use a single binary value, a single bit to represent that. But because we have three different values, red, yellow, and green, now we need at least 2 bits to determine that. So we happen to choose green encoded as 0, 0, yellow as 0, 1, red 1, 0. We could have chosen another encoding. For example, we could have chosen that there's a green bit, a yellow bit, and a red bit. So green would have been 1, 0, 0. Yellow would have been 0, 1, 0. And red would have been 0, 0, 1. So we could have chosen 3 bits. That kind of makes sense because, one of these output wires will be tied to the green light, one to the yellow light, one to the red light. But these kind of more compact encodings could be fed through logic, which are then, create these other outputs as well. Okay, so I'm not showing this second encoding. This is the second option. We're going to use this encoding, but you could have chosen a different encoding, and they both would work. So I've gone straight to the encoded output table, but you could first do the unencoded output table. Here we have the current state on the left. S1, S0 is first in the S0 state. Well, in the S0 state, we go back to our state transition diagram. And we see that in the S0 state, LA is green and LB is red. So LA is green, we use our green encoding here. And LB is red. In the S1 state, LA is yellow, 0, 1, and LB is still red. In the S2 state, LA is red, and LB is green. In the S3 state, again, just from our state transition diagram, in S3, LA is still red, but LB transitions to yellow. And so now we can write equations for these circuits. LA1, bit 1. Sum of products, we're going to get S1, S0 bar, or S1, S0. Using combining, we just get S1. That's for LA1. LA0, we just have the single one, S1 bar and S0. LB1, we're going to get, S1 bar and S0 bar, or S1 bar and S0. That will just reduce to S1 bar using combining. And finally, we get LB bit 0. So LB0 is going to be S1 and S0. Now we build our circuit, our finite state machine, using a logic circuit. Always start by putting the state register. In this case, we have 2 bits again, S1 and S0. Always put the clock input and the reset input. Remember that we have our current state on the right. Those are our state bits. And our next state is on the left, because at the clock edge, that next state is going to become our current state. Now we implement our next state logic, just using our next state equations. And finally, we implement our output logic, using just our current state as inputs. And we can do the same thing that we did with our first FSM. We can do a FSM timing diagram and basically simulate this circuit by hand. And we'll see that, in fact, at reset, the state goes to S0 as expected. This one's an asynchronous reset. Just after reset goes high, you can tell that the state resets S1 : 0. In this waveform, we show both the current state and the next state, as well as the outputs. And you can go through the logic and double check. We can also look at the state transition diagram to see what we would expect. So we get into the reset state, which is S0. TA is high for quite a while. And so the next state that should be calculated, well, when TA is high, the next state should be S0. And in fact, that's what it is. Next state's S0. So the current state at the clock edge becomes S0, S0. And finally, when TA goes low, we're in S0, TA goes low, and start to calculate the next state as S1. So at the next clock edge, the current state becomes S1. And so forth. So you can trace through your circuit and see what your timing diagram works out. And it should follow your state transition diagram. So remember, our finite state machines are composed of a state register, next state logic to determine the next state from the inputs and the current state, and output logic to determine the outputs from just the current state. And again, remember, in this class, we're only going to talk about more finite state machines. The book also covers milli-finite state machines if you want to read it now or later. But in this class, we're only going to talk about more finite state machines. And here's a review of the design procedure.